Welcome back to Advent of Code 2019, day 16. In the middle of day 16. I don't normally like to leave things unfinished, but sometimes it happens. So, quick reminder, we have this encryption algorithm, sort of. Well, it's not even encryption, it's, well, yeah, it is encryption. We solved part 1, and then part 2 is sort of the same, but you have to do it for 10,000, a sequence that's 10,000 times the size, but it's repeated, which is probably where the trick is. Now, I think I've been thinking about it over the past couple of days, and I think I have an idea for how to speed this up. Before I do that, though, I think we were getting a wrong answer. So that needs to be debugged. So let's see. So here we've got 10,000 sequences. So initial sequence is that. Base pattern is that. So that's part 1. We just, when we run this, it goes through them step by step. Okay. And then part 2, we start a new sequence. Offset is in there. And then we want to get the message from the sequence, so do we get the correct answer for part 1? 244. Well, this is... What's a different input sequence? Alright, how about we just go back to part 1, make sure it's still working. Input signal. Okay, how about this? That 24176. 24176. Okay, that's correct. So it's still working for part 1. Part 2. Puzzle input repeated 10,000 times. Oh, I know what might be the issue. That. Can't do that. No. It's creating reference copies of the list. So if I change something later in the list, it's going to affect all 10,000 blocks. Yeah, so... What do you do here? How do you make... Do you do like this? Sum of... Can you do a sum of lists? No. Okay, how about this? Sequence. I don't like having to do it this way. I'm sure there's a... Should we just... Let me just Google this. Python. Concatenate lists together. Just take a sequence of lists and put them, concatenate them together. It's reduce, isn't it? You want to reduce... Try using reduce. It's not something I practice much. Sequence equals reduce. Do we have to import reduce? Reduce. The function. So is it just going to be... You can't just put plus operator. Let me Google this. Use reduce to concatenate lists. Alright. You just have to write an explicit lambda. I'm sure there was an easier way of doing this. Extend? Oh, no, that's not what we want. Star operator, yeah, don't do that, because that's not actually a proper... Okay, reduce, here we go. I have to log in to read about reduce? Fuck off. I can see... roughly see what they're doing. We're going to reduce lambda x, y, x plus y. Okay, just do it that way then. Lambda x, y goes to x plus y. And then we want... Hello, DJ. I've just started on the... Well... Just continuing from where I left off last time with problem 16. I sort of have an idea how to do this now. First, I need to get it the correct answer, even though it's slow. Then we can think about speeding it up, so... Reduce. So we want... this. Reduce that. Okay, try that. Now it's going to take ages to build that sequence, but once it does, it should be faster to do each one. Well, it's about the same. We'll just have to wait for it to hit 100 then. No, because we don't have the answer for this one. Stop. So we want to try this one. Okay. Okay, so just wait for that to hit 100. See if we get the right answer. Alright, and hang on, stop. I should print sequence as well. No. Print. Yeah, the sequence is too big. Just leave it as that. Okay, so let's let that run. So in the meantime, see what's wrong with this, if there is anything wrong. So prefix sums equals 0. Thing is, we still have to do 6 million operations each time. That's still too much. It's almost 1 billion. It's doable, but booking, it's gonna take several minutes to, I don't know, up to an hour. Depends. This will have to go. Would be replaced by smarter method. So this 0044. No. Getting 0044 again. Why have we got this one? I don't think this reduce is actually doing what we think it's doing. No, it's doing the same thing. No, it's not. It's creating a new copy each time. I don't know. Let's test this out then. I don't know. So sequence equals reduce. Let's make this 1, 2, 3, 4. So that gets a sequence, and then do sequence 0 equals -5, let's say. Print sequence. So only the first element should change to -5. Oh, this is really big. Yeah, okay, so that's safe. That it's not changing any others. Alright, well. So that is the correct sequence. And part 1 sort of shows that this method works, FFT. So the problem is probably in this offset message thing. Let's have a look. Offset. Sequence up to 7. So the first 7 characters. Of the original sequence. Do I have the correct offset? I'm gonna check all these things now. Two, four, four. Oh no, that's part 1. 303673. Yeah, okay. So with that, we skip. Let's stop running this. We still run this 100 times. So we get the final output. Offset to offset plus 8. I don't actually like this method though. I mean, we can change it even though it's kind of wrong. But it's working for part 1, but how could it be working for part 1 and not part 2 if it's the only thing that's changed is a bigger message? Is there anything that would actually change here? Don't think so. I don't like this first equals true nonsense. Can we just not do that? Number repeated equals mo. Num repeated? What does that even mean? What? Maybe we should change this. Oh, number repeated means number of times a specific one of these gets repeated for each each subsequent item in the input array. There's gotta be a better way of doing that though. Let's define get sum effectively. What we're trying to do is get dot product, right? So get dot product for the jth no, we don't even need for a given num repeats no. Yeah. Pattern repeats. So given a number of pattern repeats, an index to start from, and the array is fixed. So we've got a method which tells us the product for a given number of repeats and a given index. Okay. Is basically this logic, I guess. We can extract it for now. Total equals 0. First equals true, while input index. Okay, take these out. While input index is less than us. So num repeated equals that plus 1. And if it's the first iteration, we just subtract 1 because we're starting from a different index. So actually, whoa, take that out for now. So this starts from index 1. So it'll be the input index plus the number of repeats across the length of the array. So the sum oh, wait. This isn't correct. Not always. Oh no, this is fixed by this, so... Pattern no. We don't need this at all. So on the first iteration, there's just one of each number. So if it's... So here, this becomes 0. And then it'll be input index plus 0, so it'll still be 0. Slice end. So the slice goes to the end. It goes just is a null slice. If pattern repeats is greater than 0 and the pattern we're looking at is non-zero, then we add the sum. And then we go on to the next base pattern. And we cut the slice. Alright. So if that might have fixed it. Now we want product equals get dot product of pattern repeats is going to be j plus 1. Let's call it dot product so we're clear. Dot product. Let's try that now. Hopefully we get the same result for part 1. All we did was move stuff into a method. What's this? Okay, well... stuck. While input index less than length array. What happened to... Okay, get rid of part 2 for now. Alright, it's stuck. So when you do one operation of this, we've got pattern repeats, so so for j equals 0, we want number repeats equal 1. Oh. Oh, damn. Hang on. Alright, if it's the first iteration, we should just... Alright, so block size equals pattern repeats. If it's the first iteration, then we just have to subtract 1. Oh, we never returned anything. That's also a problem. Alright, try that. 244. I think that's correct. Well, we've got to make sure. So for our input, four four zero. 440. Okay, so that's correct. And if I run part 2, it's going to be the same speed as before, probably. That's fine. Okay, it takes a while to do the reduce. But the reduce needs to be done. So how long is it going to take when we've got this massive thing? Oh, it's doing it for the large one. Well, that's going to take too long. I don't know how to solve that issue, but start with the small one. Alright, well, we can see if we get the right answer, but we haven't changed much. Now, there's got to be some major simplification here that I'm not seeing, because even doing this, creating this massive sequence, takes too long. There's 10,000 times 6 million. Let's just try and get the answer correct first, even if it's too slow. But as far as I can tell, you need that whole array. How can you skip it? Because you're taking a dot product with a repeating list. So even though you know what part of the list you care about, just these 8 characters, somewhere in the middle, even though you know that, you still, to get even one character of that, you still need to take the whole sum across the whole list, don't you? Or... Oh, wait. But I think... Actually, you don't, because... Oh, okay, hang on, I'm getting an idea. For each of those 10,000 blocks, there's only a small number of possible different sequences it could be, Because it all depends entirely on the index of the repeating pattern you're using. So, you don't need that entire array. It's still confusing though. How do we put this all together? We need lots of sub-methods. Okay. So the first thing we need to do... Well, let's see if we can get this working. Still wrong. Why do we keep getting this 0044? What is that number? It's not the right number, but it's consistent. Consistently the wrong number. What else? So it works for small sequence. It doesn't work for the big sequence. 0303. I wish they give a simpler example here. How can it be working for part 1 and not part 2 in this case? But the only thing we're changing really is making this bigger, although we're doing it in a weird way, but... So we've got really big J values. That's one of the differences here. Can we... What else? What else could be wrong? Maybe it's just as simple as we're using the wrong variable name somewhere, we're referring to the wrong thing. This is a bit of a mess here, bro. Prefix sums, that's computed here. Oh, 0306. Puzzle input repeated 10,000 times. So we keep the offset as part of the input signal. We don't take it off. Do we? Oh. Why couldn't they give us a simpler example? Zero, 1, 0, -1. We never changed the base pattern, right? I'm running out of things that could have gone wrong. Plus equal. Just bracket that. I don't think it matters. Let's put this here. Oh. Um. I don't see anything wrong. What the f- Oh no. Oh no. That should be message, not seek. It was the most simplest. Oh, I bet that was it. Let's try running it now. That. Why was that seek? Should have been message. Message is the extraction. Wait. We don't even need to do that. You literally just print message. We've got the message. There. What was that? Let's try this now. Right. If this is the correct answer, then we are one step closer, but still, I don't see a complete way to optimize this yet, but if we get the right answer here, then we're on the right track. And then the next step we can do is change this to be generic index. That would be useful. This is a really hard problem. How fast did people solve it? 20 minutes up to an hour, 8 minutes. That's quite a long time. Okay, so we need to think of everything. We need to think in terms of blocks. So we don't have one giant input list. Instead, we have 10,000 blocks. Okay. And eight, 4, 4, 6. Correct. Okay, so that's fine for the example. Of course, if I try to run it on the full thing, it's going to take absolutely forever. I mean, this step alone takes too long. It's 10,000 times 6 million or something. So yeah, clearly we can't do that. So instead, we have to... Now, how could we represent our sequence? We could represent it as a map. No, like 10,000 item array, and each item is one block. So, before I do that, though, I want to change this method to use an offset. So, offset equal offset. All right. So the base pattern index, what will that be? Basically, it will be so each of these blocks will be num repeats long. So it would be... So the number of steps we move along in this pattern will be offset divided out the pattern repeats that's how many steps we move along. Percent 4, and then that's because we go around in a circle. Or specifically, length of base pattern. Alright, so that's where we start. So if offset is 1, then in most cases this is just going to stay 0. But except for the first case, when pattern repeats is 1, it'll be 1 divided by 1, which is 1. So we'd actually start here. That's useful. Okay. Then, the other thing we need to know is initial num repeats. This will be different from all the rest. This will be basically it'll be offset minus, so you divide out all these blocks and just whatever's left, that's just how far we go into the actual block of repeats. So that's the initial number of repeats. Shouldn't be 0, because if it was, we would have... Oh no, it could be 0. Yeah, I mean, in the case we're saying offset is 1. So we start here. So initial number repeats, it's going to be 1 minus 1. But we don't want that, do we? We want... Hang on, no, this is not right. Oh no, I'm using my terminology wrong. It's not that. No. It's this, isn't it? That. Offset divide out modulo the pattern repeats. No, it's not that either. Wait, what is it? The answer to this should be 1 for this case with offset equals 1. With offset equals 0, I mean, with offset equals 0, it should be pattern repeats. So it's going to be pattern repeat. Ah, of course, pattern repeats minus is it that then? So for offset is 0, that will be 0. So just be the pattern repeats, the full thing. For offset is 1. It will be normally you subtract 1, except when offset is the same as pattern repeats, i.e. if pattern repeats is 1, offset is 1. So this actually becomes 1 modulo 1, which is 0. Then it would still be pattern repeats. It would just have moved on to the next index. Okay, I think that's possibly right. So base pattern index is that, initial number of repeats is that. So here, if first, no, we don't do this. Block size equals initial. No, okay. We basically do this, but we don't do that. We do equals initial number of repeats. Just it's safer this way. So in general, it's pattern repeats. On the first iteration, it's initial. Okay, and then we don't ever do that again. And then we just use that all as normal. So the only thing we should change here now is just have an offset of 1 always. Alright, we get the same answer. So it's going to be, we need 244 as the first number. Yes, and then we'll see if we get it for the second one, but we probably will. Okay, so that's generalized. And now that's good because we may need to do lots of different offsets for different blocks. So that method is it efficient? It's efficient for, not for the whole array, but if we were to split our array into blocks and just treat this as running on a block, that's efficient. Like, I don't think you can speed that up any further. Can you? No, probably not. Like, you need to look at the whole array to be able to compute the dot product. That's, unless you do some matrix algebra of some sort. I don't fancy doing that, but I mean, that's kind of what we're doing. Just doing matrix algebra from first principles. The next thing we want to do is just change this to be a... Well, we'll figure this out. Okay, that's right. Now, instead of one long array, I want this array to be a concept which has 10,000 items in it, or just some number of items in it. So... sequence is not this, it's this, oops, that. Alright, don't worry about part 2 for now. So it's a series of blocks, and in this case it's just one block. And we want to produce a sequence of a similar form. And then here we just want to get from the first one. Okay. Now the good thing about this is that you could have this same thing in many places in sequence, like say 100 like 100 places, but it wouldn't be replicating 100 different copies of that, separate copies of that initial sequence. It would actually be passing them by reference. So you'd only be storing 10,000 pointers, and there'd be many duplicated sequences, I would assume. Okay. Now this needs to be changed, so call this a sequence, but it's actually a series of blocks. Oh, prefix sums is different thing now. Damn. I can't really do much about prefix sums. Well, for X an array, do we want prefix sums for the individual? Prefix sums will have to be a hash table here, because otherwise we're trying to make a really confusing list. So prefix sums is table which takes the block number in this sequence, okay, it's just a table for now. So it's going to take a block number, starting index, and an end index. Or, I don't know, it could be this. I'll just do what we did before, but 0, 4 in range, length, sequence. So for each block, we create one separate prefix array. And then this time, for I block in enumerate sequence. So for each block, and then we do this. So for X in block, prefix sums dot append. So it's going to be prefix sums I dot append, not offend. Prefix sums I, the last one, plus that number. So it's just going to be replicate what we did before, but one for every block. Result, that's a separate thing. Well, result is the new sequence, so it's going to be It's going to be... just, I guess, this for in range. Let's get some numbers in here. Num blocks equals length. Sequence. Didn't we already have something called num blocks? Block size, different thing. So... okay, result is that. Alright, so that handles the prefix sums, I suppose. Get dot product for a given... oh man, this is so confusing, because how are we gonna... for now, it's just... this code will just assume there's only one block, so we're just doing it as if there's just one block. It's gonna be block num. Let's change this to, because block is confusing, change this to run size. That's like a run in poker, where it's not even the correct term. 3 of a kind or something, that's not a run. A run is where it goes 2, 3, 4, 5. Whatever, we'll call it run size. Block num. So here we just use blah, 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 sequence block num. Okay, and then we just use that instead. So always use block num here. So here we're doing for block in sequence for each block. We're just working on each block individually, and they're all going to be basically the same thing. For j in range length of block, we run this get dot product. We need a block num, so it's going to be actually, we need a block. We don't need a block num. Just pass the block in. We do need a block num. Damn it. Because then the prefix sums doesn't make sense. Okay, I. So j in range, so it's going to be length of sequence I. Expected type list got int instead. Result. Oh yeah, because result is now that. So it's going to be result I. This could go horribly wrong. Alright, try it. No. Okay, it worked. Now, it's not actually correct for more than one blocks because I don't think we've accounted for the offset changing. But let's see how fast it runs, even though it's wrong, because that'll give an idea for the number of operations. Well, this is wrong. Hang on. So sequence equals... So it's going to be, this time, we use the same. So it's going to be, we use copies. So pass by copies. So now that should be, and here we want the first. Oh, that runs a bit faster. Alright, and then the message is going to be different. It's going to be like, so we're going block num equals it's going to be offset divide out the number of length of sequence 0. So just divide it out by how many of those we've got. So then we'll use that block num. Offset is going to have to be percent equal that. Okay, and then take the messages. Okay, so this should be wrong, but it runs faster because we've got copies. Still, though, it shouldn't run faster because result. I don't see why it would run faster. Alright, we'll see. As long as it's correct for the first number, 244, because the second one, we need a bit of work here. Why would this be faster? Because it's just the same sequence, except it's now 10,000 blocks instead of one contiguous sequence. I suppose that's easier to work with, but still. Five, 4, 7. Yeah, it's wrong because we're not changing the offset each time. So when we access a different block, so offset starts at 1. So offset is 1 to begin with. But for the next block, it's actually going to be different. I am range num blocks. So for J, so after this, well, offset is actually 1 plus we don't need to set offset equals 1. It's actually 1 plus the length of a block, isn't it? No. 1 plus is going to be... So I starts at 0, so we want I times length of sequence I. If we've moved that many blocks, we rotate through the repeating sequence, like through many iterations, but the number we move through, the number of individual elements we rotate through is going to be like, you got 1 for every item in the block, but then you did that I times because we did that many blocks. So what's this? Block num, yeah, okay. That could return the right answer now? I don't know. So let's think. We are looking at blocks. No, it's wrong. It's not the right answer because we're localizing to 1 block. That's not the full dot product. The full dot product needs to be... It's a bit more complicated than that. Well, anyway, it's something. It's correct for part 1. It's not going to be correct for part 2. Because we're just doing the dot product of that 1 block with the repeating sequence. So actually what we need to change is... Oh, man. I don't even know how to do this. We're going to have to overhaul this method. I don't really want to do that now. I might not finish 16 today. How is it? Let's have another look at the site. I mean, can it really be this complicated? Let's think. The principle of dot product is not complicated, but the problem is I'm trying to do this all with code and I should really be sketching diagrams and stuff, but it's not easy to do that with Microsoft Paint. So maybe I need another break from this again, and I will actually get some pen and paper and work this out mathematically, and then come back to the stream and try to replicate my diagrams in Microsoft Paint. And try and finish this. I feel like with a diagram it might not actually be that complicated. It's just trying to juggle so many of these things in my head, blocks and inner blocks and all this stuff. As long as we keep it working for part 1. This doesn't work for more than 1 block because it's still localizing to that 1 block. It's doing that dot product with the repeating sequence and replacing those elements. That's it. What it should be doing is taking the dot product of the repeating sequence, the blocks, and then replace them in that block. Now, every block which uses the same offset is going to end up looking the same, isn't it? therein lies the shortcut, because if you have one block where you start at offset 1 in the repeating sequence, and the next block also started at offset 1, you're doing a repeating sequence against all the blocks, so they're going to end up with the same result. So really, we just got to find out what the sequence of offsets are. So the first offset is 1. The next offset, well, that depends on whatever this number is, doesn't it? This number here. Length sequence I. So you want to compute what? So it's 1, and then it's 1 plus this, and it's 1 plus this, and so on. You want to find out what that sequence is until it repeats. That's the first step. And it's that sequence is going to be at most about 600, right? Because length of sequence is about 600 in the worst case. So that's a small sequence. Once you have that, you only have to do 600 of these instead of 10,000, because for a given offset, you compute this, and then you update in your result, you put that answer not in one place, but in every place where that offset would be replicated. So for offset 1, you go, if there are, I don't know, 1,000 different places with offset 1, because it's a repeating sequence. So, oh man, we have so many repeating sequences. I don't know which repeating sequence is which. Let's say the offsets went 1, 47, 2000, 1, 47, 2000, 1, 47, 2000. So, okay, so you compute so that means starting from the first block, every third block is going to be the same in the result. So you compute it for offset 1, you do this for offset 1, and note that you should be not using block num, but the whole sequence. That's why this is wrong. And then every third, whatever that answer is, every third entry of result, you set that equal to this, so you don't have to compute all this again. So one computation of get top dot product takes a very long time. We're talking like, in the worst case, like 1 billion, but because we're ironing out these sequences, it should be smaller, I don't know. The point is you don't have to call this so many times. So we need, so get prefix, the prefix map, okay, we don't need this two-dimensional array of prefixes. Prefix sums should actually be some sort of, I don't know, memoized method which computes prefix sums in constant time. That can be done even for sequence of blocks, because I don't see any reason why not. So that has to be changed. Then we'll be able to find a prefix sum between any pair of indices in this whole virtual array that we're not actually storing in memory. Alright, so that's the first step. And then this would need to be changed to use Not block num, but the whole thing. Yeah, block num doesn't even make sense here. You're computing a dot product with this number of repeats, this offset, with the whole array. That's what this does. Block num shouldn't even be a thing here. That should be length of the whole array. Should I just make some notes here? Just in case I forget. Tood. Prefix sums should be method to compute sum across entire sequence. What's the other thing? Get dot product. Get dot product should use whole sequence instead of block num. So that relies on prefix sums existing. Otherwise, it can't compute those run sums. And then compute sequence. Don't, if I use seek, I'm gonna get confused with the other seek. Sequence of offsets and to avoid duplicate calls of get dot product. Okay, those three things in that order, because you need to do these in this order, might be the answer. Even then, though, we're still talking about millions to possibly up to a billion operations, but at least that's actually doable within, I don't know, an hour. I'm guessing, though, because of all the blocks of zeros and ones, because we're speeding up using the prefix sums, I'm guessing... Like, think about it. For really high J values here, for really high repeat values, it's going to be very quick, because you're actually just doing one huge sequence of ones. So that's just one big prefix sum, which we already store in our map. So that should be quick for high numbers of repeats. For low numbers of repeats, that's the bigger issue. For low numbers of repeats, that's where we are doing... But we're not... We need to identify... I mean, if two blocks are the same in this sequence, which is going to be the same, which is going to be the case often, then you wouldn't need to... So we need some sort of map which keeps track of which ones are the same. Because if we knew that, then we wouldn't have to compute another dot product for the other block. We just use the same answer. So sequence needs to not only be... So what if sequence, instead of being a list of lists, it's a map which maps a block, so i.e. a list of integers, to all the locations in the sequence that you can find that block. Now, if that way, so to begin with, it will literally be the input, this input here, as the key value, and that will map to the full range, 0 to 10,000. Like, that is replicated everywhere in that block. If I did it that way, then in this get dot product, we would only need to compute what? So you got this notion of local dot product and global dot product. Local dot product is where you just compute what the contribution of that one block is. And ultimately you want the global. But the global will just be kind of like the sum of, if all these blocks were the same, then you would just go for one of these and just multiply it by the number of times it's repeated, right? Okay, I've expressed too many ideas here, but okay, one last thing to do. Sequence should be a map from blocks to indices where this is repeated. All right, I'm gonna do all the figuring out offline. I think it's something like this is really complex. It can't be this complex, could it? I'm not seeing a trick to this, but I am surprised that the stats don't seem to indicate it's as hard as I'm finding it. I mean, okay, there is a lower ratio of gold stars here to silvers. But still, quite 9,000 people solved both parts. I don't know. Alright, maybe when I write this on paper, it'll become clearer. Okay, so that was another 1.5 hours spent with no solution. Okay, see you next time for more day 16.